Blended Podcasts. Brought to you by Blended Audio.
Alright, welcome to Talking Shit with Talos. This is episode 4, and we've been delving into computers, machine learning, artificial consciousness, artificial intelligence. As always, I'm joined by my co-host Pubby.
Yo, what's up?
And this episode, we're going to be furthering our discussion and diving into the world of machine learning.
Buzzword time.
Buzzword time, dude. Freaking peak sensationalism time, you know? So, really where we ended on the last episode was Turing-complete systems as systems with the ability to compute things. And we define the ability to compute as breaking something down into a syllogistic logical reduction of either true or false, and that true or false is either represented by 1 or 0. So, at this point, we've got computers roughly, and humans roughly, to be looking at the world around them and going, okay, this game, this action, this thing is a function of some sort of computation.
Yeah.
There are some sort of if this then that steps, and that can be reduced down into simplistic syllogistic logic a computer can understand. Now that computers can understand this logic and
Can do some compute.
Thanks to Mr. Arthur Samuel, we now are in 1951, and we have the ability for machines to learn how to learn. So let's break that down, Bobby, because there's a big difference between pure data input from a person and data, I don't want to call it scanning, but I mean, you know, what would you call a sort of Arthur Samuel's basic machine learning algorithm, you know? Because it is getting bits of data that it is then interpreting for itself as either good checkers moves or bad checkers moves. And this is now very different from getting data, this is good, this is face, this is not face, this is woman, this is not woman, you know?
Yeah.
So maybe we should just break down for people how machine learning and specifically back propagation within machine learning works, because really machine learning takes a lot of cues from nature. Funnily enough, its fundamental thing, back propagation, isn't a cue from nature. So, why is that? What is back propagation, and really, like, why do we use it?
So let's just first start with like what machine learning is. And so there's this kind of famous textbook by a guy called Tom Mitchell, and he kind of gives my favorite definition of machine learning. I'm just going to quickly read it because it's like super interesting. So it says a computer program is said to learn from experience E with respect to some tasks T and performance measure P if its performance at tasks T as measured by P improves with experience. So it's basically just saying that you get some experience from the outside world, you have some tasks that you want to do, and you have some way to measure how good you are at these tasks. And we say that a computer learns if, after given this experience, your ability to perform these tasks is better than it was before.
Right. So, sorry to interrupt you,
No, so that's machine learning as like a whole wide field of things.
So, I feel like we need to get into how does the computer know that it's getting better at the operation?
Sure. So there are like different ways. So for example, if you want to just recognize pictures of cats, right? You'll just count the number of times you got a cat picture, right? And so the performance measure would be accuracy. It would be like fraction of correctly predicted cats.
Right.
But there are a whole bunch of different performance measures. And as long as you're getting better according to the performance measure that you are actually measuring, given some new data, you'll say that your machine has learned from that experience.
So really, the performance measure can be thought of as like an incentive for the machine in a loose sense, you know? I mean, like the algorithm never has an engineer come pat it on the back and be like, well done, you got better. There must be something sort of inherent in the code of that algorithm that it's like, oh, okay, correct, let me move forward, you know?
And it's actually super difficult to come up with good performance measures. So it's actually a problem that Facebook and Google have. So when Facebook, I think, when they first started using machine learning to like do ad optimization, or it's for the timeline, right? When they were doing machine learning to
optimize the timeline,
to actually show you, they realized that if they were optimizing for number of clicks, you would get very clickbaity stuff, right? So you'd think that like, oh, I want to optimize the number of clicks because the more times my user clicks this thing, they might like it more. But then what the algorithm will learn is that like I can actually show very polarizing things, and that will optimize the click rate.
Well, that's essentially what's happening with Facebook, is that they've chosen their incentive is clicks and engagement, because that's what keeps users on their platform. And that's so the incentives of these algorithms can be quite simple and direct sometimes, but as we're seeing more and more, they can become quite sort of murky and complex. And so we understand that, you know, we've given these machines some sort of incentive to do something, and it's not necessarily extrapolating data on its own, but it is using data it already has to make decisions. And as far as I understand, the way it uses that data, the way it reads that data is by backpropagation.
So backpropagation is a very specific algorithm for neural nets.
Okay,
so they're like all different types of machine learning. So
the most simplistic type of machine learning then.
So no, backpropagation is actually pretty sophisticated.
Okay.
So just to kind of give you a history of the different types of machine learning that have gone into the trend, it first started off with logic-based systems, right? So Deep Blue, the chess algorithm that beat Garry Kasparov, it didn't actually learn anything from data. What happened is that IBM got many chess experts to come in and to tell them rules that they find helpful for playing chess games. And they constructed this huge database of, in this situation, do this, in this situation, do that. And then what they did is that they used ideas from logic, so backchaining and a whole bunch of other like logical like theorems and theorem provers to plan ahead given all these rules that you have. So they'll be like, oh, in this situation I should do this, and they'll put me in that situation and I should do that, and they'll chain it back and be like, well, I should make this move then now. But that type of AI was very brittle.
Yeah,
because
very basic.
Yeah. And if you've never been in a situation that has been put into the rules, you don't know what to do. So it kind of moved from rules-based AI to more, and I would call it connectionist-based AI, and connectionist being in the sense of like how the brain is connected.
Okay.
So, and that's what the whole deep learning, like neural network zeitgeist is right now. It's all about connectionist machine learning. And how it works is like you should think of a neural network as just a whole bunch of connected nodes. So imagine like 3 layers, right? And in the first layer, you'll have 3 circles. In the next layer, you have 3 circles. And in the last layer, you have 1 circle, right? And then from the first layer, draw a line from the first circle to all the circles in the second layer. and then do the same thing for the second circle, and do the same thing for so what you see is that like all the parts of this graph are connected to all the other parts.
Right, and it becomes a sort of triangular,
Yeah.
ever-increasing tree
Yeah.
with more and more branches.
Yeah, and because everything's connected with each other, what you do is that you'll try predict something, and depending on how right or wrong you are, it'll send back a signal. So if you're absolutely wrong, it'll be like, yo, you were so wrong about this, and it'll send back a very large signal. And what backprop is, it's a way of updating the information inside the neural network so that it's right on the example you just showed it if you show it again.
Right.
So if I show the same picture twice, the first time it'll get wrong, but then backpropagation updates the weights of your neural network so that if you show the same picture again, it will get it hopefully more right.
Okay, so that sounds quite a lot more advanced than sort of basic, shallow machine learning, as you would call it. And Deep Blue, what would you term Deep Blue as? Shallow
So
machine
Deep
learning.
Blue wasn't even shallow learning. It was
wasn't
just
even-
logic based. It was just following rules. And then what happened was that after Deep Blue, people were like, okay, we're going to come up with these new machine learning algorithms. So famous examples are like support vector machines, logistic regression.
Expert system?
No, so expert systems are logic based.
Okay, so there's a clear definition between a learning system and a logic-based system.
Yeah. So expert systems follow rules, and you give them data, but then they follow the rules how to get to that decision. Whereas shallow learning still tries to learn from data, and it tries to learn from the actual data itself rather than following rules that humans have made. But it was just called shallow because, in a sense, it wasn't able to absorb as much of the data as our current methods are able to do.
Okay, so it's in essence, it's a less advanced way of data. This is probably a good point to speak about data and its role in machine learning, and it's the role in the rise of artificial intelligence recently. So not everyone knows, I certainly didn't before I started researching for this podcast, that there have been 2 AI winters.
2, yeah.
There's been 2 AI winters, so correct me if I'm wrong at any point here. It started with Arthur Samuels in the 50s, and they reached a certain point with their logic machines. They were then sort of made into these things called expert systems. And expert systems were essentially designed to help very high volume logic-based processes, stock exchanges, medical services, so on and so forth. So you can think of a expert system as a system looking at stocks in a very, very simplistic manner, trying to discern very simplistic linear growth patterns and that kind of thing. Correct. Okay, cool. So that kind of was pretty hot in the 50s and the 60s.
Yeah, and it was very overhyped, actually. It was overpromised, and people said this was going to change everything.
And there was 2001: A Space Odyssey with what's the...
Hell.
There.
I haven't seen that movie.
Neither have I. It's actually really funny. But basically there was a lot of hot air in the 60s about AI, and when they realized that, well, first of all, when normal computation got a little bit better, and they could use normal computers that weren't so expert to do these things, it became a lot cheaper, and people realized these expert systems were actually pretty shit, and AI kind of died. The idea of artificial consciousness went away till the 80s.
Yeah.
Who revived it in the 80s?
What happened was there was this guy called, 2 people, McCulloch and Pitts. And they kind of designed the first mathematical model of a brain neuron.
Right.
And it was a really simple concept. It was this concept of like, I have certain variables, right? I push them through, and if the variables maybe sum together and done a transformation to them afterwards, if it was higher than a certain value, it pushed 1 or something. Otherwise, it didn't push anything. In the same way with when you have a neuron, there needs to be a certain amount of electric activity going through the neuron for it to fire off its own transmissions. Yeah,
right.
And this idea eventually turned into another really famous algorithm called the Perceptron by a guy called Frank Rosenblatt. And the Perceptron was also extremely overhyped until this really famous paper.
Well, what did the Perceptron do?
It was just a modification of the McCulloch-Pitts mathematical model of a neuron.
Okay.
It was it used backprop actually. I think it was
was it put into operation, or was it
so I think I might be wrong, but I think a very basic version of backpropagation, but the Perceptron did use backprop, I think. And what happened was that a real genius, this guy called Marvin Minsky, he showed in this paper that there were certain functions that perceptrons could never compute. And an example of one was exclusive XOR.
Okay.
XOR, so exclusive OR, sorry.
Yeah. The XOR problem.
The XOR problem. So just to explain what the XOR problem is you say you have 2 variables, A and B, and they can both be 1 or 0, right?
Right.
So if I said A or B, usually, right, the A or B would be true if A was true and B was true, if A was true and B was false, if A was false and B was true, but not if A was false and B was false, right?
Oh,
so that's the normal OR.
Yeah.
Exclusive XOR says I only want one of them to be true, right?
Okay.
So it won't accept A is true and B is true, and it won't accept A is false and B is false. Exclusive XOR will only be true if either A is true and B is false, or A is false and B is true, right?
Okay.
And the perceptron, it's a pretty basic function that's used in computers a lot, but the perceptron couldn't learn it. It couldn't learn XOR. And Minsky proved this mathematically. And he was quite a giant in the field. He was a really great pioneer in AI. And so after people read this paper, they were like, neural nets are dead. They can't do XOR. It's over.
So how does XOR relate to, let's say, a Facebook facial recognition algorithm?
So XOR was just a very basic problem. And people were like, there's no way we're going to be able to like recognize faces.
So have we overcome the XOR problem now?
Yeah, we definitely have. And how we overcome it was by making our networks deeper.
Right. Okay, so this is a good point to say that once the XOR problem was established, as you said, people thought neural nets were dead.
Yeah, they thought it was game over.
Yeah, they did die. And this is kind of why it feels like to everyone that AI is this new thing, because essentially they died until not even the mid-2000s, like the late 2000s. Like,
so I don't know the history exactly, but what's interesting is that a couple of weeks ago, there were still a couple of people that kept working on them because they just believed in them. And 3 of the most famous, they actually won the equivalent of the Nobel Prize for Computing, the Turing Award, was Geoffrey Hinton, Yoshua Bengio, and something LeCun. I don't know what his name. Jan LeCun. And they just believed in the idea of neural nets, and they weren't basically bothered by what Minsky proved. And they worked on them all throughout the AI winter, and they got them working. And
so they were the first guys to get the modern idea of a neural net working.
Yeah, so there was a lot of work by a lot of people, but I think they're generally seen as the people that worked through the winter and got our neural nets to where they are.
So do you have any idea when sort of they achieved this?
I'll say there was a landmark paper. So for image recognition, right, people used to hand engineer features. So an image, right? So I don't know for the people listening, but what you could think of an image of is as a Rubik's Cube, right? Mm-hmm. And each bit of the Rubik's Cube contains a number. So an image is this 3x3 structure where each bit in the structure holds a number of the pixel value, so your RGB values, right?
Right.
Red, green, blue. And what people would do is that they would find really clever ways of looking at these values, so features, and taking those clever ways of looking at these values and putting them into a learning algorithm. And there was this big competition, and the competition, they would get like 60% accuracy at predicting if this thing was a car or like a bridge. And in 2012, Alex Krzyzewski, I think, a student of Geoffrey Hinton, they came up with convolutional nets.
Right,
it was
which we'll get into a bit more.
Yeah, and it was the first kind of paper where they just blew every traditional method out of the water. It was such a big improvement from what other people were doing that people had to notice. They were like, okay, neural nets are here and they're staying. And after 2012, it's been like a roller coaster ride. Growth. The methods just get better every year.
Absolutely, yeah. And so, circling back to machine learning.
Yeah.
The rise of the internet and the rise of data has been pretty fundamental or instrumental in making these machine learning algorithms capable. Because the rise of data, especially data through social media and things like YouTube and Facebook and whatever, is unbelievable. There's never been any system in human history that's produced that amount of data that consistently. So
I heard a crazy fact. I think it was in 2017 where they were like, in that year, we collected as much data as we had collected in the entirety of our existence beforehand.
Damn.
I heard that, I was like, wow.
And how many of those videos are absolutely useless?
Or like cat videos on
YouTube.
YouTube.
Cat videos, freaking people cleaning their house and shit.
Yeah.
What a wonderful world we live in, dude. So that little point there kind of illustrates this entire thing with data pushing machine learning, and the reason we really have seen such a rise in machine learning recently, shallow machine learning, even machine learning that doesn't necessarily require lots of data storage. It's actually very good for now because there's just constant influxes of data for it, And as you say, after that 2012 landmark paper, that's when
AlexNet, that's what it's called, the AlexNet.
The AlexNet paper.
Yeah.
Got a network named after himself. That's an achievement. The AlexNet paper took what is shallow machine learning, i.e. something that a computer can basically extrapolate data from, but doesn't require deep understanding of the subject material, really. And they took that and used the idea developed in the 80s of the nodes, sort of to make machine learning one step deeper and one step more natural. And that one step deeper and one step more natural was neural networks.
Yeah.
And those neural networks, as we say, were supposed to imitate human-style thought processes with, well, at least human-style neurons, with positive results resulting in what could be thought of as a neuron charge to make the machine
a very basic, very idealized version. Our neurons do much more
complicated stuff than that. And if there's any biologists listening, they are obviously going to have my ass for breaking neurons down so simplistically. But for the sake of this, we can think of the neuron as firing single electrical pulses and the neural network trying to mimic this. But as you say, that was quite simplistic up until 2012.
Yeah.
And that is exactly where we'll pick up next week on convolutional neural networks, deep learning, and AI and AGI.
Ooh.
Yeah, it gets better and better. Usual thank yous, Blended Podcasts. It's been a pleasure. Blended Audio. What a wonderful studio to be working in. Thanks, Pubby, for the good information and the straight and narrow.
Thank you, dude.
Thank you, Kenny, for being our I don't know, our frickin' engineer.
Good old
And
reliable Kenny.
yeah, thank you to whoever's listening for listening. We hope you enjoyed it. See you soon.